Just to give a bit of context, I think you can think of today as kind of like putting a lot of pieces together from last week and then seeing what it means in a full quantitative macroeconomic model in the afternoon, but with a detour in the morning to really going into the details of how scaling laws work, what we should think about them, and where scaling laws is basically just understanding the way the performance of AI models, specifically LLMs, are evolving over time as we use more data and compute. So in a way, this is going to be a bit less economics and a bit more just knowledge about the way these models' performance is changing over time with respect to their inputs. But I think it's important to knowledge to have when thinking seriously about projecting forward the possibility of transformative AI. And then the rest of the week is going to be a bit more of a grab bag, disassociated from like the full just models of production and possibilities for growth that we talked about last week. Okay. So what's known as the chinchilla scaling law comes from this Hoffman et al. Paper. We've shown this equation a couple times last week, but what it says is model loss is approximately equal to some small negligible amount of irreducible loss, and then what you can think of as a gross complements combination of data and parameters of the model. Data in is parameters of the model, and the amount of compute you need to use is equal to 6 times data times parameters. A, we can think about as algorithmic progress because it tells us, as we make gains in our software efficiency, how much can we reduce the loss with less data? So you're being more sample efficient. You don't need to use as much data to reduce the loss as much. And it's worth saying that loss, when formally defined when evaluating these models, is average next token prediction error on test data. So that means, if you train the model on some corpus of text, and then when you're testing the model on a new corpus of text, what is the ability of the model to predict the next token in that corpus of text? Yeah, Burkhard. I don't think similarity across domains is being captured in the data measure. It's a good question. I don't know the exact details of how it's always measured, but I think even if two papers are like two different Acemoglu papers on directed technical change, I think we would think of those as like just two data points in the same way. One Acemoglu paper on directed technical change, and a GIF is another data point. Obviously, you're actually measuring it at the level of tokens rather than a unit of a paper. But and I should also say, there's a lot of, I think, debate amongst computer scientists about the exact form of these scaling laws. My understanding is there's kind of like a paradigm between Hoffman et al. Versus Kaplan et al., who have like a slightly different formulation. I'm not the expert to ask on that. I know Hans, I don't know if he's here, knows a lot about that. I would imagine Anson and Charles know more if you're curious to ask about that. Yeah, Pedro. The small d you can think about as just like a constant that indexes, the level of loss associated, it's almost like an efficiency constant. It's just a constant. So yeah, little d and little n are just positive constants. Beta and alpha are also going to be positive constants, but we're raising them to negative powers. Yeah. Okay. And so then we can ask, if we have a fixed compute budget R, and we want to train a model to minimize loss, how much data and how many parameters should we use for the model? And if you set up the loss minimization problem, given the fixed compute, you're going to get these solutions for the optimal amount of parameters, the optimal amount of data to use, where this G term that appears in both is constant. I'm not going to walk through that derivation because that derivation is your exercise for today. But what's important to take away from it is that, so there's this Besaroglu et al. Paper from Epoch that estimates these alpha and beta coefficients of how, loss declines as you use more data or use more parameters. And they estimate alpha and beta are basically the same, which means that if the number of parameters and the number of data are raised to beta over alpha plus beta and alpha over alpha plus beta, you end up wanting to scale them basically in proportion. And this is what's referred to as the chinchilla scaling law, that if you want to make a model efficiently trained to minimize loss given your compute budget, you end up wanting to scale data and model size approximately in proportion. And this matters if we're data constrained, because if we've scraped all the internet data and we have no more data we can give, even if we keep throwing in a bunch more parameters and compute to the models, we're not going to be able to reduce loss that much. We're going to have a bounded amount that we can reduce it, and that scaling is going to be inefficient. You can get around this a little bit. Yeah, inefficient in that you're not minimizing loss given your compute budget, basically. But yeah. You can get around this a little bit by training on multiple epochs of the same data. Like epoch there, you can literally think of, when the neural network, when the algorithm's doing these forward and backward passes, you just give it the same data multiple times. Like you train it on the same data once, then you train it on the same data again. And this costs more compute, but effectively gives you more data. However, this paper finds steeply diminishing returns to how much that's able to reduce model loss after about 4 epochs. And some people say Grok went beyond that. So yeah, that's just something to keep in mind. And these scaling laws don't just apply to large language models. It's really a property of, I think, neural network architectures in general. And so this Villalobos paper shows across many different tasks and architectures, this general power law scaling relationship holds in intermediate regimes. And intermediate regimes here is about intermediate amounts of data, given that you have as much compute as you want. So when you have basically no data, that scaling law doesn't apply. You just don't have enough data to reduce loss at all. But then once you cross some threshold, we start observing loss declining as a power law with data. And then we get to the irreducible error region once we have more than sufficient data. There also is, I should note, some statistical theory on why scaling laws should take this form. It's not just that we posit these things and purely note them as an empirical phenomenon. There's work being done to understand why model performance should have this relationship. Something to look into if you're interested in. Yep. Yeah, so this is saying suppose you always have enough compute to do the chinchilla optimal scaling. This is what it's going to look like over time. Yeah, so in this Villalobos review, where that graph comes from, he looks at 25 distinct studies that, the paper's from 2023, so obviously there's stuff that's happened since. A lot of the models are language models, but there's a bunch of vision models, specialized RL models, multimodal models, etc. And he looks across different scaling variables, parameters, data, compute. This is just a sense of basically, if you go to this report, he has a big spreadsheet of all these different papers that evaluate scaling laws within that domain. The reported exponent values here refers to those alpha and betas. So the median across all these studies is 0.28, which is similar to for the chinchilla scaling laws that Besaroglu estimated. It was 0.35. I do think it's worth noting that in these papers, the amount of training compute used is lower than what we're seeing from current state-of-the-art large language models. But I think the takeaway is just that these scaling laws are a powerful phenomenon that we have actual theory to believe is going to hold for neural network architectures and holds across lots of domains in some form. Yep. So I think Grok is e to the 25th, like 10 to the 25th flop, some coefficient in front of that, but I forget. Grok 4, that is. So I think this is an active area of discussion of, are we going to be able to scale up data using synthetic data? You might think that if that synthetic data is like not actually new information, like it's just basically a reconstruction of what already exists, then we're going to run into that multiple epochs problem. But if you think we can create synthetic data that is genuinely new data, then we're not going to be data constrained. And I mean, I think this is something that people are putting a lot of effort into right now. Okay. It's not that they're necessarily less than optimal, but just if it's easier to get compute than it is to get data, as Phil was saying earlier, you might as well use the compute, but you're not training the model in the maximally efficient way. Like that extra compute just isn't giving you much, but you might as well use it if you have it. Ignoring the fact that maybe that compute would be better allocated to post-training stuff. Like this is all talking about pre-training scaling laws. I should be clear about that. Yep. You're saying, where does this graph come from? So he has it in this paper. This isn't like actual data from a given paper, like that's actually testing it on some specific model. This is just like a stylized diagram that Villalobos presents to show how these scaling laws tend to work across lots of different regimes. If that makes sense. Phil? Yeah, so this is kind of to Berkai's question. Like an ideal measure of data would capture their similarity, but we're not always capturing that in the way we measure it. Yeah, Pedro? As I was mentioning earlier, there's like some debate about how exactly what form these should take. I think this has been converged on as like providing the best empirical fit and also having the statistical theory that supports it. Oh, you mean how you define loss? Yeah. Yeah, so I believe it's going to be like it's average next token prediction error on test data, but it's entropy, where it's like the log of the distribution of frequencies you're predicting versus the actual. Yeah. So, I mean, I completely agree. If you believe that the data is getting less and less independent that we're adding to the models, we shouldn't expect loss to be decreasing as much for a given increase in compute. We're going to talk in a couple slides about like have pre-training scaling laws broken down. I think the tentative conclusion is they haven't quite yet, but you still might expect that we're near that regime if you're very concerned about this. Mm-hmm. Mm-hmm. Yeah. So in this Villalobos review, which is from 2023, so not even like quote unquote state of the art, he does have some multimodal models in here, and there's a relevant way of defining all of this in that context. Okay, unless there's any more questions, going to keep going through. Yeah. Okay, and so scaling hypotheses are kind of like a class of ways of thinking about how scaling could get us to AGI or whatever. So there's a bunch of things called universal approximation theorems that basically tell us that sufficiently large neural networks can perfectly approximate any continuous function. And then the scaling hypothesis we're going to say is a big enough model trained on enough data on human behavior in some domain should mimic that human behavior. And that gives us a plausible path to AGI. With the note that, if for whatever reason neural network architectures are inefficient relative to the human brain, you might need much more data and much more compute than the human brain uses in order to get that AGI. But these approximation theorems are like a big part of the reason why people believe that if we just keep scaling up, eventually we'll get to something that is a fully general intelligence. Another thing that people talk about a lot is the bitter lesson, which comes from this 2019 Sutton paper. And the bitter lesson is that the only thing that matters in the long run is the leveraging of computation. So again, the idea is that really, if we want to reduce the loss, if we want to get the models really good, ultimately the biggest thing that matters is just scaling things up, both in terms of data and parameters, but overall scaling compute. However, I do think the emergence of post-training and then reinforcement learning with human feedback does show that we aren't purely trying to leverage pre-training computation. We might want to modify models so they do more than replicate the data. And what replicate the data means there is, if you're minimizing loss, you're just always able to do exactly what your training data says the next thing you should predict is. But there's might be other things we want, like, oh, the model responds morally to a moral question rather than just responding with the predicted, moral response, whether that be bad or good, given some question. And so there's a bit of a debate going on about have pre-training scaling laws broken down. Toby Ord has a couple of blog posts and also appeared on the 80,000 Hours podcast. This is a quote from his 80,000 Hours podcast appearance this summer, where he goes, what seems to have happened is that scaling laws already kinked right at the point where GPT-4 was out and before GPT 4.5. And the releases of Grok 4 and GPT 4.5, which were the two biggest models to date in terms of pre-training, both e to the 26 flops, kind of ignited this debate because people were like, oh, these models aren't that good relative to what had come before. However, I think the jump to saying that pre-training scaling laws have broken down is a bit too hasty. So there's just a good blog post by Trevor Chow and Jack Gross-Whitaker. They show that GPT 4.5 still follows pre-training scaling laws on a variety of benchmarks. And the point they make of why it's hard to just say, oh, GPT 4.5 isn't that much better than O1 or something, which might have used less pre-training compute, and conclude that pre-training scaling laws have broken down, is that now we're also doing a lot of post-training. So it's not fair to compare a model that's mostly pre-training with a model that's, half and half pre-training and post-training. You want to compare their performance given just the amount of pre-training they've done. And it does seem like in their evidence, GPT 4.5 still follow these laws. Another piece of evidence for, yep, Phil. Sure. So, basically pre-training is you have some training set of data and you do these forwards and backwards passes trying to minimize your objective function, which is this loss function we talked about. And the neural network learns the weights and all the different layers of the network in order to make predictions. And then we have this model with all these weights, and we do post-training, which refers to both things like reinforcement learning with human feedback, where you're taking the model's outputs and having a human grade it, reinforcement learning on a specific domain where maybe the model's evaluating its own answers on coding challenges or math problems or something, and things like scaling up inference compute, where you're giving the model more time to think or allowing multiple versions of the model to come up with an answer and then letting the model evaluate between them. So all of those are you have a pre-trained model that can output an answer given a question, and then you're fine-tuning it beyond that. Does that seem? I think that's true of like most of the post-training when, the original Chat GPT came out, where what they were doing was just like making sure it gave answers that didn't deviate from the answers they like wanted to appear for whatever reasons. I think that's increasingly not true, where now there's lots of post-training being done to improve performance on tasks like coding and math and stuff. But I agree with the general point that, like, yeah, you can't compare apples to oranges and evaluate pre-training scaling laws against a model where you're combining the pre-training and post-training compute. Pedro. It's can be scaffolding on top of that, and it's not even necessarily changing the weights. Like, giving it more inference time is not changing the weights of the model.
I think a good example is about worldview. So right now, if you like go on ChatGPT or whatever, ask it to help you.
I think the reason is that 4.0 has more post-training, so it's harder to do the apples to apples. I think that's like the speculation, and based on the report, they don't seem to emphasize the post-training. Yeah, like based on OpenAI's like model release card. I mean, I think don't know is too strong. We don't know for sure.
Okay.
Yeah.
Because like it didn't seem like they had a strong justification. I'm fine with it. Why would it?
Well, you might think that, and we're going to talk about this a bit more, that post-training has its own scaling laws, but it's important to emphasize that the scaling laws are you have log of compute on the x-axis and loss on the y-axis or performance. So that is going to be diminishing. Like we predict that that's a concave function, whatever, if it's performance rather than loss. And you might be on the steeper part of that function for the thing you've done less of. So you get more out of originally adding in the post-training, and it's higher returns to doing that. But that doesn't mean the pre-training scaling law is necessarily broken down. Okay. No, so the compute variable here is just about pre-training compute. Like you can think of that as like an increase in effective compute, and we might want to characterize scaling laws with respect to effective compute, which we're going to do in some form later. But thus far, the compute variable is just pre-training compute. So I mean, I'm not saying that the pre-training scaling law is the only thing we should care about, but I'm saying here's how the pre-training scaling law works. It's something to know about. If that makes sense. Yeah, and we're going to, in RL and inference scaling, I'll have a couple of graphs to that effect. Yes, though we might want to think about, is there complementarity across the two? I mean, I think there's efforts being made to do quality improvements. My understanding is that in the existing model, like the existing previous iterations of LLMs, in terms of the pre-training data, there might be like parts of the internet that have been scraped that are new parts that got added to the data set, but I wouldn't say there's necessarily been an increase in quality. But that seems right to me. Yeah. Though you might think that like of no value, it might be that some random Reddit comment is of no value if you want to answer a question about like how do I solve the Jones model. But if someone else asks the model a similar question to that random Reddit question and says you are some random Redditor, and then that data becomes valuable. So it's like, yeah, and I mean I think it's like you're trying to predict in any given context what would come next, and so in that, like if that data replicates a context that could come up, then it's useful for at least that context. And this point here, which we didn't talk about, is just kind of like a hand-wavy argument for pre-training laws continuing to hold, is that it seems like relative to the OpenAI models, Gemini 2.5 from Google and Opus 4.1 from Anthropic, are a bit more tilted towards pre-training I mean, sorry, yeah, a bit more tilted towards pre-training and have done less post-training. Yet their performance, the state-of-the-art models, is roughly similar to the state-of-the-art from GPT or from OpenAI, suggesting that, hand-wavily pre-training laws are continuing to hold. And then we'll also talk I'll have a couple graphs right now to show you that it seems like Grok 4 also followed pre-training scaling laws, though it is a bit tricky to evaluate because of the amount of RL that was used. And I also just had this note that I don't think we have great estimates out there of how much pre-training compute GPT-5 used, so I don't have anything to say about whether or not GPT-5 followed pre-training scaling laws. But so this is a figure from Grok 4, and the point is this is across different amounts of training compute, how its performance worked. And then this is across different amounts of test time compute. And what you see is that the scaling law is holding in both regimes. So like as they were scaling up pre-training compute, performance was increasing. The same was true of test time compute, but we had some type of pre-training scaling law holding in the training regime. And then similarly, Epoch has done this analysis of the GPQA Diamond benchmark, which is like PhD level, math and science questions. This is supposed to be, I mean, it's hard to know these measures for sure, but supposed to be pre-training compute on the x-axis, model or GPQA Diamond accuracy on the y-axis, and Grok 4 is, if anything, above trend. So once again, some evidence that pre-training scaling laws are holding. Pedro? I agree it's a little surprising. I mean, the reason it would be not surprising is just these are benchmarks where there's a well-defined right answer. And if loss means that you're like predicting the next word and the right answer consists of the next word, you would expect a similar sort of relationship to hold. But I do think this becomes more of a problem when we think about vaguer benchmarks that might have more like economic content to them that's not just like a right-wrong binary. Then should the same relationship hold? Maybe not. We're going to talk about that a bit more. Phil? To me, the balance of evidence is pre-training laws still seem to basically be holding, but there's definitely some uncertainty around that. Another thing to talk about is algorithmic progress. Following this paper from Anson, I don't know if he's in the room, who's going to be talking later this afternoon, and co-authors at Epoch, you can think about algorithmic progress as improvements in effective model size and data set size over time. And specifically here, we're going to think about them as exponential improvements in those effective model size and data set over time. So we're redefining, we have the actual number of parameters and data, but as time passes and we have some rate of algorithmic progress, alpha prime and beta prime, it's like we have more effective parameters and effective data. And then we're just going to denote these big A or capital A and capital B as this rate of algorithmic progress. If we plug this into the scaling law using the effective parameters and effective data, we see that we can think of algorithmic progress as factor augmenting growth in these defined A and B variables. And this is just to give you kind of like an economic sense of what algorithmic progress entails. And within here, there's two different notions of algorithmic progress. So the B is indexing what we would want to call sample efficiency, where it's like how good is your performance given an amount of data. You're very sample efficient if you don't need to have that much data to achieve a high level of performance. And the A is like algorithmic progress with respect to how effectively do you use your parameters, your architecture in some way. In order to estimate algorithmic progress, this paper from Anson estimates different coefficients of this model, where algorithmic progress is modeled like this across 231 LLMs. Of note, it only goes up through 2023, which is GPT-3. And I think their estimates of the rate of algorithmic progress are used in a lot of like forecasting exercises. I think there's probably some value in updating this work. Given the coefficient estimates for the rates of algorithmic progress, you can back out doubling times for effective compute. Remember that compute, which we previously said R, was just 6D in, where D and N are actual data and parameters, but effective compute you can think of as being a combination of, you know, actual compute and this enhanced notion. And their finding is that in this period, 2014 to 2023, algorithmic progress caused effective compute doublings every 8.4 months, with a confidence interval from 4.5 to 14.3 months. Yes, sorry. It's just saying, like, if you had held compute completely fixed just from algorithmic progress, it's like we were to double effective compute every 8.4 months. Actual effective compute increased at a higher rate because we were also increasing actual compute over this time. And they do this Shapley value analysis to figure out how much of the algorithmic progress is in the B, which was the sample efficiency, versus the A. And their central estimate is that algorithmic progress is responsible for approximately sample efficiency is responsible for approximately 88% of algorithmic progress. However, if you look at like the actual coefficient estimates for these alpha primes and beta primes, they're not individually significant. It's only jointly significant that we know like the combination alpha prime plus beta prime is positive, so we're having algorithmic progress over time. But we can't really say with much confidence whether that algorithmic progress is coming in the form of data augmenting or parameter augmenting growth. And then also just for some additional, to Phil's point earlier, the overall increase in total effective compute is about algorithmic progress and the actual scale up of physical compute. And they estimate that from 2014 to 2023, our overall increase in effective compute is about 2/3 physical compute, 1/3 algorithmic progress. So this is just measuring the former notion. Like, can we get just as good performance using half as much compute? I don't think we know that it's symmetric, and I do think that's an important question. And the reason I emphasize that these coefficients are not individually significant is we might think sample efficiency, the factor augmenting growth in how much, you know, the BT term next multiplied by data is really important. For one, if we're data constrained, you know, and we can't scale up data, the only way we would reach AGI is by having these sample efficiency improvements. And additionally, you might think even once the model's like perfect on the existing data, if when AGI comes, we're inventing new tasks in the economy, if it's the case that they've gotten there just from us scaling up data and not improving sample efficiency, humans would still have an advantage in these new tasks where we're relatively data impoverished. And I think this is one argument you could make for why, even if we get an AGI, to the extent new tasks are created, there's still a role for human labor. For some evidence of this, you know, this is very hazy, and I think there should be large confidence or uncertainty bands around this, but roughly, maybe humans are something like 4 orders of magnitude more sample efficient than algorithms. Some evidence of that is that GPT-3 is trained on 10,000x more words than the typical child hears. And the idea there is they're roughly equally good at producing language. But in order to do that, you need 4 orders of magnitude more data for GPT-3. Similarly, Waymo cars are trained on 2,000x more driving hours than a human drives before they pass a driving test. It's different if you count the simulation data that Waymo cars used. So again, that's why this 4 orders of magnitude should be taken with large uncertainty bands, but roughly gets you in the same range. Alpha code is trained on 10,000x the coding data of competitive coders. In all of these estimates, it's hard to know how to think about the role of evolution, because it might be that evolution has given us like training data that we're not counting when we're just doing this, how much does a human see in their lifetime exercise? But I think it's pretty reasonable to say that it seems like humans are significantly multiple orders of magnitude more sample efficient than current algorithms. Maxime? Yeah, I mean, I wouldn't necessarily use the universal function approximator language, but it does seem like our architecture is able to get the same performance out of less data. I don't think I said it was dismal. The bitter lesson, the sense in which they call it the bitter lesson is like, oh, you think you're this brilliant computer scientist who's going to figure out these better algorithms and like figure out how to construct an artificial mind. No, the only thing that matters is just throwing more compute at it. Whatever you do doesn't matter. However, this section on algorithmic progress is kind of, oh, now actually like figuring out the algorithm stuff does matter. But the bitter lesson is this notion that like we don't really care about anything other than scaling up pre-training. Yeah, and well, I mean, no, because it means we need like lots of energy and resources as opposed to just being able to figure it out.
Oh, I know how to programming my model.
We mentioned this Ethan Davidson review paper recently. They show across domains, data requirements approximately halve in each year. If you just take that rate of progress and take this 4 orders of magnitude, which is super uncertain, literally, that would imply that AI will be as sample efficient as humans in approximately 13 years. But note that even if we think the AI gets to be as sample efficient, if we're still not as good at giving the AI the data that humans get, we wouldn't necessarily have AGI from just training an equally sample efficient algorithm. And this is just a table from that Ethan Davidson review showing across image recognition, language translation, game playing, large language models, algorithms writ large. We're able to make these sorts of sample efficiency gains. But what's important to understand is that the sample efficiency gains tend to be domain specific. So when we figure out some like great new algorithm for how one of these models can learn from chess data, we can't just use that same algorithm from chess data to then make these models more sample efficient language or whatever. Yeah. So are you asking, can we measure, like I think what I'm confused about there is there's, with something like Wolfram Alpha, it's not learning from data. It's like stuff that's been hard coded in. So I don't know that we could. So yeah, I think that would be like, suppose like, I don't know, maybe Tim can correct me if this is totally wrong, but like suppose we give the LLM some like prior in the architecture on how like math works, then maybe it's going to be more sample efficient at learning from mathematical examples. I don't know of work that's like exactly what you're talking about, but I think it's reasonable to think that could happen. Yeah, so when we get to this AGI win section, we're going to think about like, all of human capacity. How much compute does that take? Does that give us a benchmark for thinking about how much compute we would need to get a fully general model? I think I said what I want to say here. 2 other things that might be important are in-context learning and online learning. So in-context learning refers to like literally like you can think in your conversation with ChatGPT, as you're going through the conversation, it's starting to understand better like what it is you're asking about. And it might be able to like dynamically in that context learn and come up with better answers. And I think anecdotally, it kind of seems like this is more sample efficient than pre-training in the sense that like, okay, you ask it to help you make the slides for this course. And at first, maybe it gives you a terrible answer, but then you say, oh no, like I want it more like this. And it can actually pretty quickly correct itself. And that seems like it's being pretty sample efficient in the way it's learning. Like I give it an example of, oh, here's what Phil's slides looked like yesterday. Now suddenly it does better. However, so you might think, okay, maybe we just expand the context window for these models, and so that it can do like lots of this learning in context in order to get the models better themselves. The problem with this is that the costs don't work well. So you can think of the cost per a given token of output as being some fixed cost plus a variable cost that's proportional to the context length up to that point. So that means the total cost is going to be proportional to the roughly to context length squared. That's going to get very expensive. So even if you thought in context learning was super sample efficient and powerful, it would be very expensive. And additionally, this comes with the problem that you're not in context, the model's not actually updating its weights. So it might be really great at learning in context in some conversation, but this doesn't then just generalize to the next conversation a new instance of the model has. Though perhaps this could be solved by like, if we had so much compute that constantly the model was being trained on all the conversations that were happening at once, maybe we could get around this. Online learning is when, different from in-context learning, is when model weights are continuously updated as the model learns in the real world. You can think about this like how with humans, we have some pre-training model weights for how we learn language, but then when we learn language, it's like robustly true that neuron architectures reform, whatever. The problem is, like, you can have online learning algorithms that allow for models to do this, but the problem is there's no way for the model to update the weights that it would, that the way it can't update weights as it wants to in online learning without undoing the post-training you've already done to get the model to perform in the ways you want. So I think this, could be something that's fixed, but right now it doesn't seem like online learning works very well. And we're gonna break for 10 minutes. Be back here at 12:10. Parker's gonna remind us about what he said last week and then say a few more words on algorithmic progress, and then we'll get into the rest of it.
Gotcha. Then this is just a reminder of what Cheryl and I worked on and presented on last week about where you might think this algorithmic progress comes from. Probably a reasonable first step is just guessing that it comes from like a Jones model type equation where you have some research input, which is a CES between labor and compute, and ideas are getting harder to find as people try to come up with different algorithmic improvements. Before we were talking about automated researchers, but probably in the past we haven't had any automated researchers, so Z is like pretty much 0. Maybe Cursor, Claude Code is like a tiny little fraction or something. And yeah, there's possibly different amounts of substitutability between compute and labor for how we go and create this algorithmic progress. All right, so what I'm mostly going to talk about is just a little bit of a methodological point about Epoch's estimates of algorithmic progress. And I just think that they're a little bit more sketchy than a lot of people assume. I think it's a great first pass, but I think we should have very wide uncertainty about how much algorithmic progress there really has been. And this is just one precise point about why their estimates could be badly wrong. So the intuition is what Zach was presenting before is assuming that algorithmic progress is just perfectly exponential, right? It was assuming that BT is literally just some exponent, some exponential function of time. But that's kind of surprising. Why would you expect that it's literally perfectly exponential? First, just across time, but then also within the same time period, probably not everybody's using the same algorithms. So for example, in 2023, probably OpenAI has way better algorithms than some random researcher at MIT because they have private research they don't release, etc. So we're going to generalize the algorithmic progress term to include some error term. So instead of saying it's perfectly exponential, it's like approximately exponential with some error, which is mean 0, but it's high for OpenAI, but it's low for academia. And then I'm just going to show how that can really mess up your estimates. Why can that mess up your estimates? To make things simple, let's just take the Hoffman loss equation, but assume the irreducible loss is 0, and let's just assume that the number of parameters you have is infinity, so we can just focus on the amount of data, because that's going to make everything linear, so it just like makes things a little more familiar, easier to deal with. So just plugging in exactly what Zach had before, but just plugging in for what D effective is, given that we're going to make this assumption, you get this as your data generating process for the loss. Now, because we made those nice assumptions on E and N, everything, we can take logs and everything is linear in parameters. So we kind of have this like familiar from an econometric standpoint, like linear equation. But now we have this extra term. The epsilon is appearing because there's the algorithmic progress is not perfectly exponential anymore. And if you just remember from like econometrics, if your data generating process is this, but then you estimate this linear equation, you essentially have an omitted variable. And in order for that to be not a problem, you need that omitted variable to be exogenous to all your other data. And so in this particular case, that would be assuming that having better algorithms is uncorrelated with having a larger training data set size, which seems to me very implausible, because you would think, OpenAI both has better algorithms and trains much larger models, has much larger data set size. So I would have like a pretty strong prior that this exogeneity condition does not hold, which means you're going to mess up your estimates of beta and also this beta year condition, which is just like the multiplication of these terms. And some weak evidence on this from this that is, I really want to emphasize, is not very strong at all. But the beta that they estimate in the algorithmic progress paper is 0.04. But in this experimental paper we talked about, it's 0.37. So it's actually different by almost 10x. In theory, you should think they're almost the same number, but maybe one of the reasons they could be different is this is experimental, so there's no possibility of this kind of selection bias type thing to come up. But here it is, and it's biasing the result downwards. But they could be different for many, many other reasons. That's just like one possible reason that they're different. Phil? Yeah, it's just the chinchilla scaling law replication paper. Gotcha. And I don't want to be, this is kind of just a general problem, I think, with estimating algorithmic progress with observational data, is that, we didn't get this data by random. People chose their compute in response to their algorithms that they observed. And kind of, it's not just like this one epoch paper is going to get messed up by this, but just like any time you're trying to estimate algorithmic progress, I think you're going to have to deal with this. And it's a bit of a challenge. So maybe it means we should be trying to estimate algorithmic progress like just with experiments instead of trying to infer it from observational data. And just to get an intuition about how this can create bias and what is the direction of the bias, I just ran a simple Monte Carlo where we just take the data exactly from Anson's paper and Epoch's paper, and we just simulate that error term to various degrees of correlation with data set size, and then just see how much bias you get in what direction you get. And so in this simulation, we see that as the correlation becomes negative, you underestimate beta, and then accordingly, you overestimate algorithmic progress. Because essentially, you're saying, well, actual scaling is lower, so where did that all progress came from? Well, I'm going to assign it to algorithmic improvements, even though that isn't where it actually was coming from. So this is why if their beta is understated, like actually it would be like way over here for 0.04, that you might have some way overstated degree of algorithmic progress. But these actual numbers like depend on the simulation parameters that I chose, so you shouldn't take it that seriously. It's just a general lesson of what direction does the bias go. It is also very plausible that their estimates are like way underestimated. Maybe the rate of algorithmic progress is much higher than actually stated. I just think we should have a wider confidence intervals than just like the 3x number per year that they give. Yeah. 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 Yeah, for sure. I think there's like a ton of possible random variation here. Maybe people have different compute prices because of something. Maybe they just have, different marginal utilities of money because like, if you're an academic lab, you just like can't, it's like impossible for you to scale to like 100 billion or something. Yeah, I would be shocked if there isn't an instrument. But given that you can run experiments, I think just to flag, I think Hans is running experiments to do this. So like that's kind of like if we could run the RCT, like let's just do it, I think. Instead of like using some sketchy instrument. Pedro? First, I think it's without loss of generality to make it additive, right? Because it can just be any, like, I didn't take a stance on what distribution it is. So it could be correlated. Well, no, it can't be correlated because of the way the approximation works. The way to rigorously define this error is like, say that if you progressed BT on Y, it's the residual. And that's like well-defined. And making it additive is just nice because you have like exponentials and stuff. But like if you wanted to define it as multiplicative, like you could get some probably similar results. Go ahead. Well, I guess it depends on what you think if you think this term is positive or negative. This argument makes it seem like it would be negative, but like a priori, I would think it was positive because people who have bigger data set sizes also have better algorithms, so my a priori guess is that this is positive, but that doesn't mesh with this, so then I get confused on where does it go either way. I just think you should, it's just it's either positive or negative.
Okay, so now the big question we want to use scaling laws to answer is, when are we going to get AGI? They tell us about historical rates of progress with respect to compute and algorithmic progress on well-defined problem spaces. Thus far, we've talked about literal model loss and predicting the next token, and then some kind of well-defined benchmarks. What we want to know is the rate of progress on economically meaningful metrics, in particular, how on the path to full automation, or what percent of like when we scale up compute, how does that translate into productivity, automation capacity? I think there's roughly 3 approaches one could take to go from this discussion of scaling laws to thinking about the economic notion of AGI. One is this rationalist approach where you're using top-down reasoning about how much compute and data are needed for a general intelligence, and then interpolating from our current levels of those things to fit some function of how close we are. Another approach you could take is what I'm calling crude empiricism, where you track progress on things that are imprecise or not direct measures of what we care about, but are somewhere between just like model loss and like actual automation to date. Finally, we could measure what we care about, which is like for a given amount of compute, how much does this translate to automative capacity, productivity? The problem with that is it's only really feasible once AI starts making progress on those metrics. So if AI hasn't automated any % of the economy, we can't come up with a scaling law with respect to how much compute translates into how much automation. So we're going to go through each of these approaches in a bit more detail. So this rationalist approach, I think, is best exemplified by what people call bioanchors. The rough idea is to try to show from first principles that X amount of data and compute would produce AGI. It's pretty assumption laden, and it's worth noting that most of this data was done kind of the early 2020s. We're not really there anymore, where we had a big data regime. There was much more data available than there was compute. Now we're kind of in a world where we think there might be less data than there is compute. So these approaches might tell us how much compute we need if we're able to scale up data correspondingly. Bioanchors refers to the idea of reasoning from how much computation is needed to train various biological systems to project, okay, if we use the same amount of computation on these models, we would get a model that performs similarly generally. And the most famous instance of this is this 2020 report from Ajaya Kotra, where she considers 4 different sorts of bioanchors. We're not going to go through all of them in a lot of detail, but the approaches are estimating the total computation done by a human brain before the age of 32. This is what's called the lifetime anchor. The total computation done by all brains, like all neurons, over the course of evolution. And then you can also look at the computational power of the human brain and the computational power of the human genome. So that's not looking at how much computation is done, over the course of its history, but how much computation can it do in the case of the human brain or the human genome. Roughly, we're not really going to talk more about 3 and 4, even though they are interesting. You can think of this one as, number 1, the lifetime anchor as providing a sort of lower bound, and the evolution anchor as kind of providing an upper bound. But I think that's sometimes people talk about the evolution anchor as saying, okay, if we just used as much compute as was done over the course of evolution, we could simulate evolution, and thus we would necessarily get AGI. That seems incorrect to me because, existing algorithms have different objective functions than evolution. Obviously, existing algorithms' objective function is like minimize loss in terms of predicting the next token, while evolution's was something like reproduce, survive. Different objective functions, obviously different architectures in nematode brains versus neural networks. And you might also think even if the objective functions and architectures were the same, like evolution was pretty path dependent. There were lots of things along the way that made it so evolution happened the way it did. Yeah. And so people talk about it as an upper bound, and specifically the gate model and the Davidson model, which we're going to talk about more this afternoon, basically use the evolution anchor as an upper bound. But for the reasons Phil said, and these other reasons, we might think that's actually not a good upper bound. And, doing post-training to get AGI to behave the way we want would be different from just getting it to have the capacities of an AGI. And getting online learning to work, getting sample efficiency, et cetera, may require additional compute. Lifetime, because it's what occurs within a human life up to with the rough idea that by the time you're 32, you are an AGI. Your human capital could develop to do any job if you train it on the right amount of data up until the age of 32. Something like that. And so the units of computation, which we've been throwing around, but just to make precise, are flops, which refers to floating point operations. And a floating point operation is just one addition, subtraction, multiplication, or division of 2 decimal numbers. Across these 4 approaches, Kotra gets a median estimate and an uncertainty band for each different method. The lifetime anchor gives you the lowest median estimate of 3e to the 27th flop, while the evolution anchor gives you the largest estimate of 1e to the 41 flop. So it's obviously a huge range of 14 orders of magnitude just within the median estimates of each of these approaches. If you use the uncertainty bands around each of those approaches, you're going to get a much larger range beyond 1e to the 50 flop. Again, previewing what's going to come later, in both the gate model and the Davidson model, when they parameterize how much compute is going to be needed to get AGI, they tend to give a range about 1e to the 33 to 1e to the 41. And I think both of them have a median estimate of 1e to the 36.5 flops. And these are crucial inputs into these models. So to the extent we just don't believe what's come before, we might be pretty skeptical. But if we think there's some grounding for it, then maybe we should take it seriously. It's important to note that these are effective flops. So like when we're improving algorithmic efficiency, even if we only have 1e to the 31 flops of like actual physical compute, algorithmic efficiency might be able to get us to effective flops of 36.5 or whatever. Okay, so cashing out this approach a bit, the AI 2027 project and this Dean section from it estimates that circa 2025, March 2025, global AI compute is 10 million H100 equivalents, which is roughly 3.15 e to the 29 flops per year. They estimate that global AI compute is going to 2.25x every year based on historical rates of progress. We're getting a 1.35x from chip efficiency, which you could think of as like the A term. Or no, ignore that. Global AI compute will 2.25x per year from both increases in chip efficiency and just the raw number of chips. If you were to just extrapolate this, we wouldn't get to the e to the 36, 3.2 e to the 36 flops until 2045, assuming all the AI compute in the world was then used on a training run. That's probably unrealistic in that, Grok 4 is the biggest training run to date at roughly 5e to the 26 flop, which is only 0.002% of the e to the 29 that we have available. If you just use that ratio, that would say, okay, we only get enough compute on the biggest training run in 2053. However, this is conservative if you think that A, we're going to concentrate compute, so the more of it will be used for one training run, and we're going to have algorithmic progress improving our amount of effective compute. If we take the estimate that Parker has told us we should have lots of uncertainty around of algorithmic products, 3xing effective compute every year, then we would get to 3.2 e to the 36 in 2034, 1.6 e to the 39 in 2037. So, it's reasonable to think this range of very high compute numbers could be reached within a decade or so, effective compute numbers. And then the way these models work is they say, okay, if we need this much compute to reach full automation, how much automation do we get from intermediate amounts of compute, y, less than x? And both the Gate and Davidson model have a notion of an E-flop gap. And basically the way it works is you start with some arbitrary and like truly pretty arbitrary estimate, like even less grounded than these biological anchors estimate of how many E-flops, effective flops, would be needed for 20% automation. And then you just parameterize some function that says, okay, between the 20% automation and the 100% automation threshold, how much automation do you get? So this is just context to have for later when we're going through the Gate model. And now we're going to move on to approach 2, but basically this is the way you would go from biological anchors to thinking about when we're going to get AGI and how much automation that implies along the way. Approach 2 is this kind of crude empiricism where we look at imperfect progress measures. As I'm sure you guys have seen, every time an AI model gets released, the lab has like a model card where they show off its performance on a lot of different benchmarks. And as mentioned earlier, like these benchmarks that are not actually just model loss also tend to follow scaling power laws. The problem here is that we just can't translate performance on benchmarks to something economically meaningful. Being able to be accurate on AIME or on MMLU, what does that mean in terms of automation? Who knows? And more particularly, this Schaefer et al. Paper shows that downstream metrics, which are like more closer to actual measures of what we care about, are harder to predict with scaling laws because, for example, in a multiple choice test, your in order to correctly predict what the scaling law is going to say, you need to know the predicted probability mass on incorrect answers as well, which makes it harder to extrapolate. But these are just two examples of how we have scaling laws on existing benchmarks from pre-training compute. Another kind of class of this approach is to see if there's some sort of G, general intelligence factor, which explains how model performance improves across benchmarks as they scale. There's two papers that do this in slightly different ways and both find evidence of such a factor. The way you can think about this is you take a given model with a given amount of compute, you measure its performance on lots of different benchmarks, and you do a principal component analysis to extract like how well it's performing across all these domains. And the first principal component, you could think of like the general intelligence factor of that model. And they do these, like these do line up pretty well with scaling laws and perhaps provide us with something a bit more interpretable, though it's still a bit hard to know exactly how you would extrapolate them. But this is just showing that like, as you scale up compute, this first principal component follows a sort of scaling law of it. Like, so it's not just that performance on an individual benchmark follows a scaling law, but this general ability to perform across benchmarks follows a scaling law. Another version of this approach would be what Leopold Aschenbrenner does in his situational awareness report. And this is like a hand wavy, but perhaps useful exercise where you say something like GPT-2 to GPT-4 was roughly going from an elementary schooler's level of intelligence to a smart high schooler. And that was 4.5 to 6 orders of magnitude of scaling. If you think that the gap between an elementary schooler and a smart high schooler is equivalent to the gap between a smart high schooler and an automated AI researcher or engineer, which maybe you do think that, maybe you don't, then 5 more orders of magnitude would get us to that automated AI researcher. Yeah, as the point says, this is pretty vibe-based. Grok 4 was 1 to 2 orders of magnitude larger than GPT-4. Did we see the progress along that progression, like along that scale? I don't know. But it's been somewhat influential, so it's important to be aware of. And now we can then talk about, well, actually, we're out of time. So we will get to approach 3 in the afternoon. Okay, so just to recap, we want to go from thinking about scaling laws to thinking about when we can have AGI in the economic sense of full automation. We talked about 2 of the approaches you could take, the rationalist approach, which Tim put a helpful comment in the Slack about, and the crude empiricist approach. And I do think Tim's comment is worth reading because there are reasons you might think this rational, what I'm calling rationalist, and I don't mean rationalist in necessarily like the rationalist community, more just that it's very like first principles reasoning. There's reasons you could think it's kind of made up in sci-fi, but I do think it fits with, as what Tim put in the Slack suggests, it's able to match this pattern that as compute has increased, performance has increased at, remarkably well predicted by these scaling laws rates, and in a way that led some people to be able to kind of predict this progress ahead of time, and perhaps that's serious evidence to consider when extrapolating forward. But now we're going to get into approach 3, the idea of measuring what we care about, things with actual economic content relative to compute inputs. So skipping ahead. We've talked a little bit about this before, the meter task time framework. I've mentioned it, and then Arjun gave us more detail on it in his presentation. But so there's this task time framework where you measure how long it takes a human to do a certain task. Then you figure out what percentage of the time different AI models can complete the same task, where there's a well-defined, you either completed the task or you did not complete the task. The tasks in the meter suite are machine learning engineering problems, software engineering problems, cybersecurity problems, and general reasoning problems. And what meter has found is that for both the model having an 80% or a 50% success rate, models' time horizons are doubling approximately every 7 months. So they can do twice as long a task at either an 80% or a 50% success rate every 7 months. And for example, GPT-5, so this graph, Meter released an updated version of it after the GPT-5 release, has a 25-minute time horizon for 80% success rate, meaning that tasks that take a human 25 minutes can be done by GPT-5. Tasks that take a human within these sets of tasks, 25 minutes, can be done by GPT-5 80% of the time, and the time horizon is 2 hours and 17 minutes for a 50% success rate. And as you can see, how well models fit to the trend on this trend is somewhat remarkable, not necessarily something we would have predicted ex ante. You can think of it as its own sort of scaling law. Of course, the difference here is we have model release state as opposed to compute on the x-axis, but those things can be mapped to each other. And then what AI 2027 does, this report I mentioned earlier, is takes this task time trend seriously and thinks about how can we extrapolate to AGI using it. The key input for them, because what they're really interested in is a software intelligence explosion, is what time horizon and reliability would an AI system need to have on this Meter task suite in order for there to be a superhuman coder, which they define as a coder that is able to overall do as good a job as the combination of all human programmers at an AGI company at their current work. And how they come up with this number is truly just they reason about it and come up with a number. There's not any empirics or anything. And so amongst the two people who come up with numbers, one says you would want it to be able to be 80% successful at 10-year tasks as their point estimate with a huge uncertainty interval. And then Nikola Jerkovic says 1.5 months, with also a huge uncertainty level. But they both think that 80% is the right reliability threshold to focus on. This is from the AI 2027 report. But their source for those numbers is them being like, we kind of think this makes sense. I mean, they have like a paragraph explaining it, but it's not that much more than that. If 80% success rate is the right level, and you just extrapolated the Meter time horizon trend from the previous slide, this would imply we get to that 1.5 month threshold in 2032, or the 10-year threshold in 2036. And at that point, we have a superhuman coder, and the software intelligence explosion takes off. AI 2027, it's just briefly worth going through, actually comes up with more aggressive timelines, thus the eponymous AI 2027, based on the following line of reasoning. So RE bench are a subset of the tasks that Meter uses on their task time analysis, and their tasks which are AI R&D tasks with objective scoring functions. What AI 2027 argues is that once the models saturate performance on RE bench, meaning that they're better than the 95th percentile human, we should expect algorithmic progress to speed up 1.05x to 1.6x. And they think once we reach the 8-hour time horizon, RE bench will be saturated. So then when you combine that with the fact that horizon doubling times seem to have decreased in the last 2 years, which just for reference, if you look at this graph, it seems like maybe we've gotten a little bit above trend. This is the 80% graph. That horizon doubling times have decreased is clearer in the 50% time horizon trend. So I think it's a bit strong to say we know for sure horizon doubling times have decreased, but there's some evidence of it. But AI 2027 wants to take that evidence seriously, and then they simulate across distributions of these different parameters, and they get 3 people come up with their own numbers and simulate across distributions, but the median arrival of the superhuman coder who instigates the software intelligence explosion would either be 2027, 2028, or 2032. Karan? Well, so it's really not as clear on the 80%, which I think the 80% is maybe what we should be looking at more. But if you look at, I should have had the figure as well. If you look at the 50% version of this graph, then it's not like this looks a bit more just like, okay, we've shifted to a different level. But the other one looks a bit more like it's a different trend line. And Meter tends to present the 50% first and then the 80% later on. I don't know. Any other questions about that? So that's, again, just one way of taking something that has more economic content and extrapolating to a timeline. Another piece of evidence that I haven't seen much discussion about, but I think is quite interesting, not something you can necessarily directly get a timeline from, but in the GPT-5 model report, OpenAI released these metrics of how well GPT-5 did on, one, replicating internal pull request contributions. So that's actual pull requests that were done by OpenAI engineers, where the actual pull request was held out of the training data. And then they call that PRs, pull requests. And then this other metric of how well GPT-5 is able to do internal research and engineering bottlenecks encountered at OpenAI, each representing at least a 1-day delay to a major project, OPQA. And so this is the pull request data. What we see is the performance of OpenAI o3, ChatGPT Agent, GPT-5 Thinking, and GPT-5 Thinking Mini. I think the two takeaways there are, one, the models can do these pull requests almost half the time. That's pretty impressive. The second takeaway is, on this small domain, we don't see obvious evidence of improvement, though again, that's not necessarily evidence that like pre-training scaling laws have broken down or whatever, because there might have been more RL compute in O3 or what have you. However, on these OPQA problems, basically the models don't help. I mean, they're getting it 2% or 1% of the time. But personally, I think that's a pretty interesting number, because you might imagine if the models could actually do these tasks that represented at least 1-day bottlenecks at OpenAI, then we would really have to start seriously thinking they're speeding up the AI research and development progress in a significant way. Doesn't seem like we have evidence of that yet, but I think that'll be an interesting metric to monitor in future model releases. Another case of translating compute into something with economic content. Yep. So I mean, they don't give us much detail on this. It's not like they've released a report on exactly how these are. It's like a 1-page section of the full GPT-5 model report. Probably that's a reasonable interpretation, but I actually think from what they say, I just don't know the answer. Like if it's the easiest tasks or not, they don't make that clear. Yeah, they might, I don't remember exactly. They might give a little bit more context about exactly the class of pull requests it is. Maybe worth looking at, but I don't, yeah. So Ali Murali has this paper, which we've talked about a little bit before, but I'll just go into more detail on how model scale translates into economic outcomes, where those economic outcomes are professional translator task productivity. He runs an RCT with 300 professional translators using 13 LLMs with different levels of training compute. The finding is that per 10x training compute, task time in doing the translation task decreases by 12.3%, output quality increases by almost 0.2 standard deviations, and overall productivity, which is measured in earnings per minute, so it's like actually economic productivity, increases 16%. This is his figure of model training compute versus productivity on the right. As you can see, it's a fairly noisy fit, but the upward trend is clear. And if you were to go back to last week's lecture on the Acemoglu-Holton's theorem approach and used the fact that we expect productivity to increase 16% for every 10x in training compute, and also used existing trends on how much models are scaling, if you hold fixed the 20% automation exposure for Malandu and all, you get to 7% productivity growth for the next decade. So this isn't a win is AGI, but it's a way of translating actual scaling laws to something with economic content. The ideal world, we measure across compute scale up how much automation occurs. As mentioned, the problem is there's just not enough automation that has occurred to make this meaningful yet. Possibly the numbers Bharat presented last week, if we continue to monitor those as models scale up, we might be able to get some real data on this, but I don't think we have it yet. So those are kind of the three approaches. Just to kind of backtrack and say a little bit more about RL and inference scaling. There's, as mentioned, lots of scaling is being done, or lots of compute resources are being put into post-training, reinforcement learning, and inference these days. Inference compute follows similar scaling laws where performance is linear in log of inference time, which is like log of compute used for inference. Scaling laws for RL are a bit more uncertain, though there's a slide on it coming in a second. And then here's a figure of different amounts of inference time used versus the score on, I actually don't remember what metric that is, but it's some metric. And what you see is of interest is we have a log x linear y relationship for the models in terms of inference compute. But for a human, we have much better gains than that. As we use much more time on these tasks, we do much better, like our own performance scales at a much higher rate. But these are similar sorts of scaling laws to what we saw with pre-training. It is important to keep in mind that from an economic perspective, inference scaling is going to be totally change the unit economics for firms and be much more expensive because it's marginal costs rather than fixed costs. We can think about how much can we trade off inference compute for pre-training compute, which Anson's going to talk more about in the gate model. But Villalobos and Atkinson have this paper where they experiment with existing models, varying the amount of inference compute they use versus the amount of pre-training compute they use, and get that you have what's called total effective compute, which is a function of pre-training compute times inference compute raised to this power 1 over m, where m is 1 to 2. So that implies that extra inference can substitute for 1 to 2 orders of magnitude of pre-training compute. We define the inference compute on a range of imin to imax, or iota min to iota max, because beyond 2 to 6 orders of magnitude, we stop improving performance. Yes, Phil?
It sounded like you were saying that that equation implies that extra inference can substitute for 1 to 2 orders of magnitude of training. Are you saying 1 order of magnitude more inference can substitute for 1 to 2 orders of magnitude training? I feel like it could go the other way.
Yeah, it goes the other way. It's worded wrong. It goes the other way in the math. Yes. 1 to 2 orders of magnitude of inference give you 1 order of magnitude of pre-training. Yeah. Yeah.
And that's only true within the range of 2 to 6 moves.
Yeah.
Because beyond that, it stops.
It stops output. Yeah. So we could use 4 ohms less of pre-training if we use 4 to 8 more ohms of inference. But beyond that 4-4 trade-off, we're going to stop being certain. Yeah.
Does that mean that
I mean, if you formulate it in terms of the percentage of the overall costs you're spending, yes. But if you're just doing it in ohms of compute, then it's like this. Yeah. Does that make sense? Yeah. And this but Turing machine note is a comment that Phil has made to me where, this is what we observe with existing models. The Church-Turing thesis implies that if we had like perfect software architectures, we should just be able to use enough inference compute. Like there should be no maximum. We could just use all the inference compute and go through all the possible combinations and get as much effective compute as we want. But our current post-training architectures don't allow for that. Yeah.
Well, yeah, so I will, I mean, you're gonna kind of propose a new functional form on a later slide. But
Yeah.
I would just point out that, like, what Villalobos and Atkinson argue is that this power functional relationship there, right, where as you scale inference, you get, square root of, like, the
Yeah.
corresponding,
Effective.
Uh,
Yeah.
like they're saying that only holds within a band. They
Mhm.
don't say it like completely flatline outside of the band.
Yeah.
And it could just be that, like, yes, outside of that band, you're using your inference really, really inefficiently. So it's not, there's no contradiction between the point that with the right wrapper, you just use an LLM as a Turing machine. It's like lots and lots and lots of inference to any feasible computation.
Yeah. It just might be super inefficient. And then in terms of RL scaling, post-training scaling, since DeepSeek and O1, it's become increasingly important. There's speculation that Grok 4 spent as much on RL compute as pre-training, though if you follow links 1 to 2 there, it seems like 12 to 20% is more plausible. Like I said, we don't really have very good scaling laws for RL compute. I think the best piece of evidence I've seen is this one figure from Trevor Chow, which he took from OpenAI's releases, which suggests that across O1 and O3, as they scaled up post-training compute, there was, log of x-axis, linear y-axis, traditional scaling law performance on AIM. So I think this is something that people need to look into more, like how to come up with scaling laws for RL, but this is some evidence that there's something like that going on. And then finally, to present just a toy model that kind of gives you a flavor of the dynamics we're going to see in richer detail in GATE, taking seriously this sort of scaling laws framework. Suppose that total compute resources double every 6 months. There are 4 uses of compute, and you have to allocate your compute across those 4 uses. We have pre-training compute, compute used on algorithmic progress research, inference time compute, and post-training compute. Both post-training and algorithmic progress compute and post-training compute are both used to improve the efficiency according to Jones-style production functions. So we're abstracting from the fact that there are researchers in the process here. We're just saying there's some level of algorithmic efficiency, there's some level of post-training efficiency. As you put more compute resources into it, you get more of that level of efficiency. And then total effective compute in this case is going to be given by our level of algorithmic progress on like pre-training compute, the actual physical pre-training compute, and a gross complements combination of inference compute and post-training efficiency. To talk more about that functional form, this is kind of an abstract notion of post-training efficiency, where, as we were just talking about with Phil, if you could have pre-training compute and pre-training efficiency just be 1, but if you were to have the optimal architecture, ZT, like you had this really efficient post-training architecture, and you just scaled up inference compute, you'd get as much effective compute as you want. We might think that within, there's some evidence within our current paradigm of post-training technology, reinforcement learning, like the ZT term, or post-training efficiency, is a complement with pre-training compute. And in Phil's talk, where he was talking about parallelizability, we've seen some evidence that inference compute is also a complement with pre-training compute. But we also want to accommodate the fact that if we're taking the bioanchors framework seriously, pre-training effective compute alone should be sufficient for increasing effective compute, which would suggest a functional form like this, where we have gross complements between post-training efficiency and pre-training compute, and that aggregate is itself gross complements with inference compute, but the pre-training compute still multiplies on the outside, adjusted for its efficiency. that's just a comment on what we might think this effective compute production function actually looks like. But going back to the simpler one, if we just want to plug some numbers into that, suppose we start with the 5 times 10 to the 26 flops that were used to train Grok 4, and we want to know when do we hit 10 to the 33, to the 37, or to the 41 flops. Just assume for simplicity that we allocate a fixed share of compute to all of these sources so that both efficiency terms grow at the same rate as overall compute. Then we're going to reach 10 to the 33 in 3.5 years, 10 to the 37 in 5.7 years, 10 to the 41 in 7.9 years. And that means we would cross Kotra's median anchor of when we get AGI just before mid-2031 using this number. And again, I think this is just kind of a way of back of the envelope seeing how these richer models like Gate model and Davidson model, the Gate model being what Anson's about to present to us, get to us reaching full automation very soon. And unless there's any questions, we'll now go to Anson. Maxine. Yeah, so Gate is going to have more specifics on that. And I'm going to talk a little bit more about the costs of what these compute scale-ups would be in the finance lecture the other day. I don't have like a super specific answer to give you right now, but I agree that's very relevant.